All right, happy Thursday afternoon, everybody. Thursday after we should have like a Thursday afternoon song that we all sing. No, what? No, you're just not with that idea. Thursday pizza. I would agree that's a better idea. Songs are cheap though, like really cheap.
We just get money from the department.
Oh, good luck with that. We should, but we still have to pay for that extra large pizza. I've discovered pizzas are more expensive here.
They are.
Like compared to Boston, even, which is pricey on things. Like, I don't know what the deal is. I'm disturbed though, because we like order pizza, cheap dinner. No, why? Pizzas here are weird too. Just go buy candy. Okay, I can do that. That'll work. Let's see. So 1 week from right now, we have an exam. Let's cancel it. That'd be great. Yeah, if we cancel it, you don't have to take it. I don't have to grade it or write it. It's starting to sound like that's win-win both for me, and then a win for you. That's a win-win-win. Oh. Sounds like a good way to get fired or something. I don't know about that. Only if you get caught. Wow.
Why are people to tell on you if you get a state?
Or not if you make it
Make it a homework? What? To pay me?
Take home assignment.
Homework 29. Give me $5. Yeah, I don't think we can do that. No. No. You really don't want to take this exam, do you? Even though we couldn't do it, I am curious what the price would be. What is the price to get out of an exam? I feel like it's pretty high.
but you can
What
put
the hell
online.
is high?
I can do what online?
Exam, you can do that online.
I can do the exam online. Why would that be nice? So it's open book. Ah. Open book exam. Have you had an open book exam in a physics class yet?
No.
Technically, yes, and technically no.
Open note, not open book.
Open notes. Huh. Kind of. You get one page. Yeah. That's not fully open notes. Even calling it a cheat sheet seems a little weird. It's like allowed cheating. I don't know if I go for that. I don't know. So you will be allowed a cheat sheet once again next Thursday. Just the front side. On the final exam, you'll get to use the front and the back. Ooh, no, fantastic, right? I will be posting an equation sheet over the next day or two, just so you know what I'm going to give you, so you know what you're going to put on the page you're going to use. And with regards to exam coverage, does anybody remember where the last exam cut off? Was it 25?
I think it was 49.
Right before capacitors? That sounds right. Whatever chapter that was, which between the different editions of books and things, who knows? So we're going to go a little into chapter 29, but here's the good news. Concepts only from what we talk about in chapter 29. So I'm not going to test you on any problems. Anything that is from chapter 29 will appear in the multiple choice. Okay? So I have just a little bit more I want to do in chapter 28, but then we're going to spend the rest of class today talking 29 stuff. And we will maybe even do one problem, but you don't have to know how to do that problem on the exam. Reasonable enough? Your question. How do you prepare for the multiple choice? You know, I get this question a lot. I have yet to figure out a good answer, which is sad. Not just this class, but many classes at many different levels. I don't know. Some thoughts. Start with the multiple choice we have in lectures. You're thinking, like, well, that doesn't do me good. That's just... But then take it a little farther. There's typically 4 incorrect answers. Figure out why. Make sure you completely understand why the other 4 are incorrect. And then after that, I would take each one of the multiple choice questions in class and find I don't know, maybe 2 other people that you want to sit down with and identify what is the topic that this is addressing. And then like completely flesh out that topic together. What is everything that we know about that topic? And if you run into something, you're like, well, I don't know this about the topic, or I'm curious about this, or I'm confused about that one part of it that was in the notes, then dig into it more, ask me questions, ask me other questions. That's a thought. Videos from other teachers online, sometimes just hearing the exact same concept explained in a different way, even though maybe you're like, well, I kind of got it, but I'm going to explain it. Just hearing something else in sort of like maybe unopened to other understandings, just hearing it that way. Magic pills, magic multiple choice pills, you know, of which there are none. That might be useful. You're thinking like, that sounds good. I wish I had magic multiple choice pills, but I just don't. Take your time on the multiple choice. They're typically 30% of the test, so they should use 30% of your time, reasonably speaking. So I think a lot of times people just, it's like, ooh, the answers are all here, they'll be easy, and then you miss a lot of multiple choice. Go ahead and just like look at the clock, set a timer. Yeah, 30% of my time will be devoted to this, and make sure that you're looking for both that one that you're gonna pick. That's like, if you 80% understand, you jump toward that one. But if you really understand, there's another answer that's actually correct. Trying to figure out what those last 2 are, the one that's almost there and the one that's all the way there, can be helpful. I said a lot of stuff. I don't know that any of that was useful at all, but there are some things. I wish I had a good answer to that question. What else was I going to tell you people? I'm not even sure now. Chapter capacitor through what we do today, whatever that was. But I'll send out an announcement that definitively states what it's over. The format will roughly be about the same. Some problems, some multiple choice, and a 70%, 30% distribution.
Next class I review.
And Tuesday we'll spend reviewing. Okay? Yay! So next week is all just test-related stuff. Okay? So I will post something with like some review problems or whatever before Tuesday's class. I have to find some review problems, and then I'll send that to you, and then we'll all do them together. It'll be loads of fun. All right? So today, let me start with this and just kind of quickly talk through what I'd already given you and give you the solutions so you can make sure that you're able to get the answers. And also do part B, which I didn't put any info about on the screen. So we had this very lovely circuit, which is still hiding behind all of my writing there somewhere. And the first step in solving this was to identify every different current that's in the circuit and give it a name and direction. So if you just look at places in the circuit where it's possible for the current to split, notice here, there's 3 different directions coming out of that junction. If I go over here to the other place where the current splits, there's 3 different directions out of that junction. That tells me there are 3 different currents in the circuit, and each one of those branches needs to be identified and named. So I decided that the one that goes around the top here, I just decided it would go from right to left. Doesn't matter, just pick a direction, it's fine. I called that current 1. The one that goes over to the left and down around the bottom part, again, I chose that direction. Pick the opposite direction if you want to, that's fine. I called that current 2, which leaves this 3rd branch down the middle that I called current 3 and said it went from left to right. So just identify 3 different currents, name them whatever you want, pick any direction you want. They don't even have to make sense. If you look at the direction and it's like, wait a minute, everything is coming into this junction. It's probably not going to happen, but at the end of the day, it doesn't matter, okay? Once you have that, remember that for every 2 junctions or 2 nodes, you get 1 equation from the junction rule, okay? So looking at the one here on the right, you can see I've drawn this with I3 and I2 coming into it, and they're adding together, and out the other side comes I1. So, in other words,
where is it? Down here. I1 equals I2 plus I3. Notice if I look at the other junction, I can see that I1 is coming in and then splits up between I2, which goes around the bottom, and I3. Again, I1 equals I2 plus I3. Both of the junctions give me the exact same equation. So from the junction rule, we get something that relates to currents and the way that they split up. From the loop rule, you're just looking for closed loops. It doesn't matter which ones you choose, you just need enough to get enough equations for the unknowns. The three unknowns here are these three currents, so I need at least three equations, and I already have one. So 2 loops will give me 2 additional equations. So I decided to just sort of go around this top little loop, and for the second one I decided to go around this bottom sort of misshapen loop. If you wanted to say start here and go all the way around the outside, that's valid. If you want to make a figure 8 through this thing, that's valid. It doesn't really matter. Just things where they start and end at the same location is a closed loop. So, taking a look at this top loop, I'm starting in the top right corner and going around. You'll see that the first thing I run into is this 4 ohm resistor, and I'm going downstream with the current I1. That indicates a negative potential drop, negative for the resistance times the current I1, okay? The next thing we come to is this 12 volt battery, and I'm going from negative to positive, so that's a step up of 12 volts, so positive 12 over here. The only other thing in this loop is going across the 2 ohm resistor with the current I3, so that's also negative, and it's negative 2, the resistance, times I3, the current, and then I'm back where I started, so that all has to add to give me 0. Are you starting to feel okay with these loops, at least a little bit? Yeah.
Can you, really quick, if your I3, like the one that I drew here, if it points in the opposite direction, what would that look like?
If it points in the opposite direction, but I'm still analyzing in the same direction I just did, the only thing that changes is this sign. Yeah. Every time, these are always going to be the same terms. It's just a matter of positives and negatives. We'll flip. Okay? Let's look at the other loop. For the other loop, we're starting here, and you get an example of this sort of already. As we go across that 2 ohm resistor, I'm going against the current flow. So that's 2 times I3, positive 2 times I3. The next thing we get to is around here where I go from negative to positive across the battery, which is apparently 8 volts in this problem. So we get a plus 8. And then the last thing is across this resistor R, which it says is 8.5, and we're going with the current. That's downstream, so we put a negative sign, 8.5 times I2. And then I'm back where I started, and I get 0. At this point is where the fun begins, which you will have to do in the homework, but I won't test you over this part on an exam, just because everyone knows that level of algebra is a slightly different amount, and it's not really important to the physics. If you wanted to, you can go through the whole process of being like, ooh, I can take this I1 and plug it into here, and then like solve this for I3 and plug it into there, like mash all the equations together with substitution. And it's a bit of work, and it takes kind of a long time, but eventually you can get answers for currents I1, I2, and I3. There are easier ways with matrices. You can use a function on your calculator to just like punch in the 3 equations, and it's like, boom, here are the answers. All of those are perfectly valid. I don't care, okay? So if you can figure out how to do that or use your calculator for it, you should get, let's see, they only asked for 1 of these, so I don't know what the other 2 are. First of all, I have to open the right slides to tell me the answer. Ooh, let's see. It looks like the current through the 2 ohm resistor, which is current I3, should be 1.19 amps. If you get that one, you're probably well on the road to getting the other 2 correct as well. Okay? I3, which is the current through the 2 ohm resistor, should come out to be that. If you're working on it over the weekend and you get stuck or you're just not getting that answer, send me your work. Let me take a look at it. I can see what's happening. Hey, pictures are happening. How you doing? Just blocking everything. Yeah, I don't want to be in that. Gotta take a picture now. There we go. I didn't even think you're terrible. Yeah, I'm just ruining your phone now. You can delete both of those if you want, and when I'm not paying attention, you can take a picture. You got me? Just crop that out, you know, or annotate it, whatever you need to do. What's that? Mine or yours? Yeah. So let's see. Part B. What is the potential difference between A and B? So they've labeled 2 points here, A and B. And this will allow us to use just a little bit of the loop rule to solve this problem. Okay? So what we're going to do is say that there is some potential at point A. I don't know what it is. I don't really care what it is at this point. Okay? And I'm going to go along a path that leads me to B. So I'm going to start here and just sort of follow this path right through that resistor over to point B. Okay? The only thing that I encounter when I do that is this 2 ohm resistor. We've said that current I3 is flowing through it, and if I analyze it in that direction, I'm going downstream, so there's a potential drop across that resistor. And that's the only thing that happens before I get to point B. There's 1 voltage drop between the two, which means I can just write part of a loop and say that minus 2 times I3 equals the potential on the other side, which is the potential at point B. So instead of going all the way around the loop so that all the ups and downs add to 0, I'm just saying that if I start with whatever I have here, and then I have whatever change is caused by this, I'm going to end up with whatever I have on the other side. Okay? It's going to be a different value because I haven't gone all the way around back to point A once again. Once we do that, we can solve for exactly what they're looking for. So I'm going to rearrange this way and say that VB minus VA, and that is the potential difference between those 2 points, is equal to negative 2 times I3. And I3 is that current we found before. So minus 2 times 1.19, that looks a whole lot like about negative 2.37 volts. Okay, just using a little part of a loop to find that. And yay, another homework problem is done. Oh, by the way, I won't be assigning chapter 29 homework until later, so you don't have another assignment due before the exam. Okay? Any questions on anything that's up there before we do the last little thing in chapter 28 and then talk about magnets? Yay, magnets. Yeah.
So intuitively, can we just say that the only thing that is connected between A and B is that resistor, so we could just get rid of the next one and just take minus 2 I3?
You could. It's the same thing.
Okay.
Yeah. Or you could do the longer thing if you wanted to and do what I did, except pick a longer path and go around this way to get there, or go around several times and just end up over at point B. All of them should give you the exact same answer. Okay. Anyone else? Can we just pretend today is Friday and just cancel everything for tomorrow? Anybody got any complaints about that? Have a 4-day weekend? Oh, that sounds pretty good. I don't know about you guys, but I'm excited about this upcoming 3-day weekend. Yeah, 1 extra day. If every weekend was 3 days, how much better would life be in general? You know, just switching from 5-2 to 3-4. You know, oh, that'd be fantastic. Alas, we should make that a referendum on the next election. Like, get rid of daylight saving time and then change every weekend to 3 days.
Rewrite the whole calendar.
Just the whole thing. I'm liking it. Why don't you get on that? You all vote and change things in the future. Then I will thank you. I'll be like, yay, 3-day weekends all the time. So let's see. Just a couple of slides on measurements. When you're dealing with circuits for real in the lab, which I know that you've already done, and probably you're using equipment and you're like, I don't know, they told me to use this thing like this, and you gave me a number and you put it on the thing and then you got answers. Is that kind of how it felt? Yeah, that was about right. Okay. Let me see if I can explain a little bit about the instruments you're using and how they're meant to be used, and why when you use them in that way that they actually work and give you something that makes sense. So first of all, The instrument that measures current, we already saw on a previous slide, is something known as an ammeter. An ammeter because, well, it's measuring amps, right? That's kind of hidden in there, amps for ammeter. The way an ammeter works is that you have to arrange it so that whatever you want to measure is passing right through the ammeter. It's almost like if the current is a river, the only way I can tell how much current is flowing by in the river is to actually put myself in the river and like feel it all flow by, okay? So an ammeter needs to go in the current, let the current pass through it, and then it can tell you how much current is in that spot. So if we had a circuit that looks something like this, right, and all of a sudden I very much want to know how much current is passing through the wire at this location, the only way I can find out what the current is to put a device there that will let the current go through it. So we take the ammeter and rewire the circuit so that it is exactly in that spot so that the current just passes right through it, and then the needle says, yay, there's this much current here. If I want to know the current somewhere else, like maybe here, I have to disconnect everything and reconnect the circuit so that the ammeter is right here in series with that resistor. If I want to know it over here, I have to put the ammeter right in the circuit in between the resistor and that particular capacitor. So ammeters go into the circuit as part of the circuit to measure current. Now you might be thinking, oh, wait a minute, how does that even work? Seems weird that if I want to measure something, I have to like put something else in the circuit to measure it. Doesn't that just change everything? Kind of. You're right in your thinking that measurements can change the thing you're measuring. In fact, we can't really measure anything without in some way touching it. Really? Really? Even think about if we wanted to say, I don't know, use a microscope and just look at something. And maybe we were able to look at it and just like put it next to a scale and say like, hey, this thing is this far across. To measure something in that way, you have to bounce light off of it. I've interacted with the thing I'm trying to observe because I actually touched it with something. And inherently that has the potential of changing the thing I'm trying to measure. So anytime we're making a measurement of something, we try to touch the system in a way where we have the least amount of impact so that I'm not measuring something different when I step into the system and make the measurement. So in this particular case, what we do with the ammeter is it's built such that it has very, 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 very low resistance, okay? It's resistance that changes the potential, right? Potential drops when current flows through a resistance. So if I can make this have really, really low resistance, then the circuit really doesn't care. I haven't changed the equivalent resistance in the circuit, which means I haven't changed the current that's passing through the circuit. And I've touched the system, I've looked at it, I've made an observation, but I've minimized the amount of change in the system by keeping the resistance very, very low. That makes some sense? Maybe a little bit. Are you alive? Yes. Okay, there's like 6 people in the front. You're all alive right here. That's good. Like as we go back, I can like literally see it as I go back. It's like, that's what you look like going toward the back of the room. It's fantastic. All right. So let's see. The other thing we can measure, voltage or potential difference. For that, surprise, surprise, we are going to use a voltmeter. Again, the unit is just hidden right in the name of the instrument. A voltmeter. With a voltmeter, we do things a little bit differently, and I'm going to explain this 2 different ways of thinking about it. Notice it says there, connect to 2 points in the circuit between which you want to know the potential difference. Well, that sounds a little bit strange and weird. Just keep in mind that when we're dealing with voltage, we're dealing with a difference in potential between 2 different spots, which means I'm going to make a connection in the circuit to those 2 spots where I want to know the difference in potential. So the way that I like to think about this is not like, don't imagine these things actually being connected. And you might have even in the lab like had almost like needle-like probes. Did you have something that was kind of like that? Maybe a little bit? Where sometimes you could make a physical connection, but most of the time it was just like these long needle things, and you sort of just like touched into the circuit in different places to find the potential difference. I think of a voltmeter as not being part of the circuit, but being something that's on the outside. And if I want to know the potential difference between one side of the resistor and the other, I just sort of reach in with the voltmeter and touch those two spots, and it tells me the difference in potential between the two. So without having to rewire the circuit, unlike the ammeter, if I want to know the difference in potential for the battery, we touch the voltmeter to those 2 points. If I want to know the difference in potential here, we touch those 2 points, et cetera, et cetera. It's like a probe that's on the outside of the circuit reaching in to find things, okay? So ammeter and voltmeter work very different. Ammeter has to be in the circuit letting the current pass through. A voltmeter sits on the outside and sort of reaches in to make measurements, all right? Another way of thinking about that is that, well, really it's connected in parallel across the 2 points where I want to make the measurement. So in this particular case, the voltmeter is in parallel with the resistor, and I want to know the potential difference across the resistor. Technically, that's true. Yeah, maybe you agree with that, okay? Which means that when the current gets to this point, it has a choice. It can say, ooh, I think I'll go through the voltmeter, or it can say, I think I'll go through the resistor. If we want to not change the circuit and change the thing we're trying to measure, we would very much like none of the current to go through the voltmeter. If the current goes through the voltmeter, well, then I'm changing what the potential difference is here, and all of a sudden I've changed the measurement just by making the measurement, okay? So what we do in this case is give this instrument a very, 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 very high resistance, like crazy high, ridiculously high, instead of ridiculously low, such that when the charges get to this point, they're like, voltmeter? I don't think so. And almost none of them decide to go that direction, and then the circuit behaves just like it did before I made that connection, and I haven't really made a change, okay? Ammeters have low resistance, voltmeters have high resistance, all right? Ammeters get built into the circuit, voltmeters sit on the outside and probe the circuit from beyond, okay? Which brings me to the third one, and that is measuring resistance, which, surprise, you use an ohm meter. Again, just the unit is sitting there in the name of the thing that you're using. And in this particular case, you have to measure the resistance of a resistor outside of the circuit when it's not built into the circuit. And the reason for this is, and I don't think I have a slide for that, is that an ohm meter is actually a little Ohm's law device. When you make a connection to a resistor, it looks something like this. So let's say I have a resistor and it's not connected to anything. It's just lying there by itself. When I connect it to an ohm meter, here we go, this is my ohm meter. How you like that? It's beautiful. What is really hiding inside the ohm meter is a couple of different things. There is sitting inside of here a potential source, a V, and also sitting inside here is a little ammeter. Okay? So in other words, it's a little device that builds its own circuit around the resistor. And what it can do is say, okay, I'm going to pass some current through the resistor, and I'm going to apply a voltage and measure the current that results, and from that, V equals IR, I can solve for the resistance. So it's like a little Ohm's law device that creates its own little circuit with a resistor. So if you try to do this, like when it's all connected to all this other stuff, now I've got like this whole system where there's like the battery inside that, the battery in the circuit. You're going to get screwy measurements. Nothing makes any sense, okay? So the ohm meter sits outside the circuit, makes its own circuit with the thing that you're trying to measure, which is the resistance of a resistor, okay? 3 different measurement devices. They all work different in a very different way. And let me just point out, you might have had something in the lab called a multimeter, which is just a combo device for all 3. which is kind of nice. I don't know what kind of equipment you have. A lot of times these are yellow for some reason. Did you have yellow ones? They're like this big. Red? Why red? Were they all like padded on the outside with like this rubber stuff that looked all industrial, like you could drop them? No? Okay. Bummer. What brand were they? Ooh, you almost said a word I was. Something cheap, probably. Oh, that's sad. Huh. I'm used to using Fluke. You look like you were about to say something that started with an F. Maybe it wasn't Fluke. I don't know. Yeah. I don't know. For whatever reason, the ones I've always used are like these big. I like that they're called Fluke. It's almost like your measurements are a fluke, and that's just kind of depressing in a way. Whatever. And then just by changing the dial, you're essentially changing between these three different modes, and you can do everything with one device, but you can't do it all at the same time. So a lot of times we have dedicated voltmeters and ammeters to kind of take care of that part while using the multimeter to kind of handle other things on the side. That is the end of chapter 28. Yay, go us. Yes? What is that? Chapter 29. I know, chapter 29. No chapter 29? Just a little bit of chapter 29.
This is it.
This is it?
Yeah, that's it.
One slide of chapter 29.
You said little, you never specified how little.
We're going to do some chapter 29. Just because after today, let's see, next week we're not going to do anything new. And then we have a break for a week. And then finally after that, we get back to having class. And we have 4 more classes of new material after today.
So isn't it counterintuitive to learn something?
I know, why are we trying to learn when we just want to take you the final later?
Well, let me ask this. What do you want?
No
No final, no midterm.
No final, no midterm?
No,
How,
take home.
how is that related to what we cover in class today?
But, okay, you should give us, whoever shows up to class the rest of the semester without any
Let's make it
absences.
realistic, just take home. Online. We have another classes online.
It kind of feels like I should just go in the next room and finish the lecture. Just let it project. You all can do whatever you want to do. Because apparently nobody's in the mood to hear anything new today. Do you like magnets?
Yeah.
Magnets are cool, right? A little bit? Just about everything I'm about to say is concept stuff, okay? So if you can just like handle like, okay, he's not gonna hit me with the hard math. Can you deal with that? Just ideas. Let your mind open.
Philosophy.
And then philosophy of magnetic fields.
There you go.
Yes, okay? And then in 2.5 weeks' time or whatever it is, we'll come back and revisit all the math-related things with this, okay? So first of all, I should give you a new symbol. Hold on, I gotta open my notes, chapter 20, whatever this is. 9, but my notes are from a different textbook and they say chapter 27. It's all so confusing. Let's see, the magnetic field has the symbol, shockingly, B. Magnetic. Magnetic? I don't know. There needs to be a B in there somewhere. Magnetic field. It is a vector, the magnetic field. You might remember we had an electric field. This is going to be a similar kind of idea, except it relates to magnets and things. All right? The magnetic field B. So first of all, it is a vector, just like the electric field. Its unit in happy physics units terminology is the Tesla, which we use capital T for. And this is not like, Tesla like with a trademark. No, it's not Tesla Model S or 3 or X or anything else. There's a truck coming called Y, I think. None of
Don't
this.
forget about the roadster.
No Roadster, none of that is happening. No. These are the dreams we apparently all have, but alas, no Tesla. The other unit is less exciting. Sometimes we'll use the Gauss. And all of you have bad memories of Gauss.
Yes.
Gauss and his law and his surfaces and all those kind of things. Yes, I know. The Gauss, which is capital G, and I should point out that the Gauss is just 10 to the minus 4 Tesla. So we just use Gauss typically when we're dealing with really small magnetic fields. It's a slightly more convenient unit. So to give you some examples, first of all, a refrigerator magnet. If we just took sort of an average refrigerator magnet, it has a value of approximately 100 Gauss, which is 0.01 Tesla. Okay, so that'll give us some basis. We're kind of used to that. Those are about the size or strength of magnets that if someone just gave you a pile of magnets to play with and let you go, ooh, magnets, like they would be of about that strength. Okay, maybe a little more, maybe a little less. By comparison, we can look at the Earth's magnetic field. And notice I put it above the refrigerator magnet. I'm going to list things in increasing order because the Earth only has about a half a Gauss. The Earth's magnetic field is quite weak. The Earth's gravitational field technically is quite weak. There's just a lot of mass there that makes it kind of add up so that it's somewhat significant. If you think about it, when I put something on the fridge with a refrigerator magnet, it defeats gravity and the gravitational force. And apparently the Earth's magnetic field and force as well, because the stuff stays on the fridge and doesn't fall to the ground. So just a tiny little refrigerator magnet defeats the Earth in two ways. So from now on, anytime you stick something to the fridge, you should be like, ha ha, take that Earth, you know, or something, all right? Because you've defeated the Earth in two ways. Let's see. We can create relatively strong electromagnets, which we'll learn a little bit more about later on. This is a combination of both using a natural permanent magnet or a magnetic material like we see below, together with a magnetic field that can come from electricity, and we can make things that are around 2 Tesla. Or we can take that exact same idea and use superconductors, which you don't really need to know what any of this is. I just want to point out some of the range. Superconductor magnets of around 10 Tesla. And the last time I checked, and I'm sure this has gone up quite a bit since then, there's a lab at Florida State that specializes in magnetic fields. And last I looked, they were up to about 35 Tesla, but I bet it's probably 60 or 70 by now, because it's been a while since I looked at that. So we can create really strong magnetic fields that are way, 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 way stronger than what we get on the Earth. Yeah.
Do you happen to know what an MRI is?
An MRI? I don't, but someone can Google search for me real quick. If I had to guess, I would expect it sits somewhere between strong and super. I bet it's in the single-digit Tesla. Your question.
There's a 2015 article about a magnet in MagField's lab, pulse field facility inside Los Alamos.
Mm-hmm.
Currently, they created a 100 Tesla.
100 Tesla we fit.
Yeah.
Fantastic. What did they do with it?
2006. They're just researching, so.
Okay. Strong magnets. There's interesting things that could be done with strong magnets. If I remember correctly, a few things that come to mind: levitation, like maglev trains. That's something that use a magnetic field to actually support the weight of a train. I think one of those labs levitated a frog in a magnetic field, which apparently didn't hurt the frog in any way, but you know, you can imagine a frog's just like, ha ha ha, what's happening? You know, hopefully the frog wasn't wearing anything metallic, because things would have been kind of sad then. Yeah, it's not good. But I don't think frogs generally wear jewelry of any type, so probably didn't have any, like, you know, broken bones they had to repair with rods or no, probably not. Let's see, what else can we do with really strong magnets? I think you can hold antimatter with it if you're careful. I feel like I've heard of other things, but I don't know what else. Maybe even working with fusion reactors, trying to contain the energy in that, but I can't remember about that one for sure, okay? So magnets, they vary a lot in strength from the Earth, which is quite weak, through to really strong ones in the lab. To give you some example, I used to work in a lab that had a 9 Tesla magnet that we could kind of play with, right? Which is a mixture of like we were actually doing research where we would take certain things and subject it to that magnetic field and look at how the electrical current flowed differently with a magnetic field, look at how the heat flowed differently with magnetic field, stuff like that, all right? But this magnet was sitting inside a vat about this big, and it was buried way down inside because it was superconducting, which means you had to keep it really, really cold, which means we were constantly feeding it, which was kind of weird. Not the magnet itself, but the container that held it. Because if it got too warm, well, the magnet wasn't superconducting anymore, and it just didn't work, okay? So we had to keep it chilled to liquid nitrogen temperatures, which are 77 Kelvin, so 77 degrees above absolute zero. So we would constantly do things like fill it with liquid nitrogen, which means all kinds of fun. Students come around, you're like, hey, let's freeze things with liquid nitrogen. This is great. I learned quickly that there are some things you should freeze and some things you shouldn't. Flowers, fine. Fruit, looks great. Cleanup is bad. Because if you freeze fruit with liquid nitrogen, it gets extremely brittle, so you can throw it on the ground and it just like shatters and goes in all directions. 15 minutes later, it thaws out, right? Not good. Now you've got melting fruit underneath all the equipment in the lab, so you could try, yeah, if you can get to it, because it shatters and goes everywhere, which is kind of sad. So we used to simultaneously like use it for experiments and then sometimes, you know, do other things with it. When we first got this particular magnet at 9 Tesla, all of the manuals said things like, if you use sharp objects in the lab, you should probably tie them down. And this was a lab where we were constantly working with like creating tiny little circuits to like put things into this magnetic field. So the whole lab is like tweezers everywhere, right? So we're like, what's gonna happen when we turn this thing on? Turns out it was extremely well shielded by the vat that it was contained within. So to feel it, you had to kind of get right up next to it, and things weren't like flying across the room. You can imagine that'd be kind of sad. Like, I'm turning on the magnet, you know, and everything just flies across the room and stabs you. So thankfully that didn't happen. But if you took like a wrench, we used to have a wrench in there that was about this big, you know, just a solid piece of metal. If you held it right up sort of against the outside of this container with the magnet, it would almost like take it out of your hand. It was one of those kind of things where you kind of hold it and you're like, whoa, look, ah. And then we would just sit around and play with that all the time because it felt cool, right? It's like, look, invisible force that's pulling on this wrench. And then go back to freezing fruit again. Grad school took a while. Yeah, but you can have fun in grad school, but you know, whatever. So we had a pretty strong magnet. It was a good time all around. That's the end of that. Let's go down here below. Permanent magnets. At this point, we're not going to discuss why some materials are magnetic. That's actually going to happen in the next chapter, so you get to worry about that in like a month, okay? At this point, I'm just going to state a few obvious things. Permanent magnets are simply materials that exist and create their own magnetic field. And we understand that that is a phenomenon that happens. We've all played with permanent magnets, and you can see here some examples of bar magnets. We all are aware as well that magnets have 2 poles. These poles are regions where the magnetic field is strongest. Regions where the magnetic field is strongest. And you can see in the case of a bar magnet, well, they're just at the 2 ends of the length of the bar magnet, one of which we call the South Pole and one of which we call the North Pole. We are very much aware as well that if I have opposite poles, if you take the proper ends of two magnets, right, and one is north and one is south, and bring them near each other, they attract. If it happens to be the same pole, north-north or south-south, you feel that repulsive force and they push each other away. Just based on these two statements, we start to get the idea that there's probably something known as the magnetic force, which we will learn about later in this chapter, okay? You might remember when we were talking about charges and the fact that they can attract and repel, just that idea led us to the concept of electric force. So a little bit later on, we're going to learn about magnetic force. Notice, if you decide to take a magnet that has a north and south pole and be like, I think I want to take the north pole home with me. And I'm going to give the south pole to my friend. You can't do it. There's no way to do it. If you just chop it in half, well, now you've just made two new magnets, just smaller, and you're still stuck with a north and south pole. This is to say that magnetic poles come in pairs. You can't have a north without a south, and when we see what the magnetic field looks like a little more, you start to understand why that has to be true. Magnetic poles come in pairs. This is different from charges. Charges, I don't have to have a north and south charge. What does that even mean? I don't have to have a positive and negative charge together at all times. It's possible for me to have just a positive or just a negative. Magnets don't work that way. I always have a pair of poles. A pair of poles. So, a couple of things here. First of all, the north pole of a magnet. The north pole of a magnet, if allowed to do so, will, let's say, lean toward the north geographic pole of the Earth. Again, if we set it free. If we put it in something like a compass, where it's just sort of floating in there and experiences no resistance, then the north pole of a bar magnet will say, ooh, I think I'm going to trend or lean in the general direction of the north geographic pole of the Earth. The south pole of a magnet will do the exact opposite, lean toward the south geographic pole of the Earth. So the way we've defined north and south poles of magnets is a little Earth-centric. You know, the aliens are going to come along one day, and they're going to be all like, what is this north and south pole stuff? We don't, on our world, we don't do it that way. Like, our magnets don't point toward the north geographic pole of the Earth. That makes no sense. We didn't even know about the Earth until just now. Hello, Earthlings. And then that's all going to get a little awkward and weird. We're going to have to redefine physics things, and, you know, alas. We'll deal with that road, cross that bridge when we come to it. So let me take this little concept and skip the next slide, we'll come back to it, to relate this a little more to the Earth and make the aliens a little more mad, all right? So notice, I just said that if I take a bar magnet and sort of allow it to turn in a compass, the north pole of the magnet will tend or lean toward the north geographic pole of the Earth, which we understand. So you can see that in a compass, it's this little thing that's formed into an arrow that is actually the magnet that's in the compass, and it points in the general direction of north. Well, there's a little problem with that. Why in the world should it point toward the north pole of the Earth? Magnets need an opposite pole to be drawn in that direction, okay? So what's really happening is if this is the north pole of a magnet, there must be a south pole that it's being drawn toward. And if we were to look at the Earth in general, we would see that the Earth's magnetic field has a south magnetic pole that's roughly near the north geographic pole of the Earth, okay? So we have a compass with a magnet. The north pole of that magnet is drawn to the opposite pole of another magnet. So that must be the south magnetic pole of the Earth. Notice, if I zoom in on these two things, they do not exist at the same location. So this point is the north geographic pole. It's based on the rotation of the Earth. It's at the location where the axis around which the Earth rotates passes through, okay? On the other hand, the south magnetic pole is off to the side a little bit. They don't exist in the same place. There is an angle between those two things. This is something that's known as the magnetic declination. Magnetic declination. And that theta is not constant. If you look back throughout time, there's evidence in the Earth that it has been a number of different angles. In fact, it's even apparently been the opposite direction at some points in our history, and there's predictions that at some point it's going to flip directions again, and nobody knows what's going to happen when that occurs. But I don't think it's something we need to worry about tonight. Okay? Yes?
Does that mean that if you were to span that into a cone, all of the area in there wouldn't be able to like measure out a compass?
If you were to spin what?
Like the angle into a cone,
Into a cone.
and you were to grab a compass and you would go in there, would it know where to go?
I think you've struck against one of the limitations of compasses. What's the plural? Is it compasses? Compi. I want it to be compi. I don't know. Really, I know that's ridiculous. Okay, so compasses only are really sort of good like through the intermediate zones of the Earth. Okay, you can see that in those locations, if I look at the magnetic field of the Earth, it roughly sort of follows the surface of the Earth, so that in that particular location, well, yeah, if I take this compass and put it here, it's going to point along the direction of the magnetic field of the Earth, which points up toward the North Pole. On the other hand, like, yes, if this thing is spinning and this is sort of like wobbling around that, like, that's fine if I'm down here, but if I start to get up into this region, things get a little weird. So the closer you are to one of the poles of the Earth, the less and less reliable something like a compass becomes. Rely on GPS. Okay, so if you're out exploring above the Arctic Circle, which I'm sure all of us do all the time, right? You're going to need more than a compass. You might even imagine a scenario where, what if you're hiking like right here? If you're hiking right there, then the North Pole, as we understand north, is on this side of you, but your compass is going to tell you north is over here. It's going to be exactly 180 degrees off if you're positioned in between the geographic pole and the magnetic pole of the Earth, okay? Now, if I'm maybe even hiking, say, right there, in the middle of that water, apparently, yeah, just ignore that. If we're in this particular region, even there you could have a problem, right? Because it's like, hey, we want to head north, which means we want to go this direction, but if you look at your compass, it's going to point over there. The farther north I get, the more those diverge, and we get more of a problem using a compass. So you can kind of imagine that when people invented compasses, they weren't hanging out too far toward the poles, and they were like, ooh, everywhere we normally travel down here works good. This must be a universal thing that is fantastic, but alas, there are limits on such a device, okay? So let's see. Let's look at the other notes that I have about this, blah, 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 blah. I said that. I should say that lest you think this is a small effect, this angular difference currently is about 11.5 degrees. So it's somewhat significant. It's about 11.5 degrees right now. It's not like they're just 0.2 degrees apart and they're sitting really, really close to each other. So there's a decent amount of physical land space up there that would have a problem with this. Let's see. Let me go back a slide just to make sure that we cover this. And then we're going to do one more slide, and then that's going to be it for today. Okay? This slide and one more. Can you handle it that long? Are you surviving? Are you going to be okay? It's like, I was talking about magnetic fields a few minutes ago, and it was like, hey, everybody's alive there for a second. And then the farther I went into talking about the Earth and magnets, everyone just kind of went, no, and just sort of lost it there in the middle. So, come back. Okay, that didn't work, but alas. Thank you. You like shook yourself a little bit. Did that work at all? A little bit? Okay, that's good. All right, just like 10 minutes. That's all I'm asking. 10 minutes, and we'll be done with this for the week. So, just like we had with electric fields, we can have magnetic field lines, which is essentially where we go into a region of space and just draw the vector for the magnetic field at every point in space. So they've drawn a bar magnet here and shown what the magnetic field looks like around that bar magnet. Notice a few different things. First of all, if I take a compass, I can use it to sort of plot out what the magnetic field looks like in that region of space. It's always going to have its north end of the magnet pointing in the direction of the magnetic field. By the way, common little issue with compasses, like the little north, south, east, west that's on there, like you can turn that any direction you want. It's kind of meaningless, right? It's only the compass, the little floating part, that actually matters. The idea is that it points toward north, so then you can turn the compass so that it lines up with north, and you can do things based on that. But it's just the little floaty thing that can spin that actually matters. So you'll notice I drew the north end there right on top of the east, because that's the north end of the magnet that's in there, all right? The background can be rotated any way you want. So you can see that if I move, well, the compass over here, notice it matches the direction of the magnetic field. If I go to the south end of this, notice it matches what the magnetic field would be doing. And here it matches that direction. So you could literally take a compass, all spaces around a bar magnet, and see what the vector is at every point in space, and see what the magnetic field looks like. And you'll notice it forms loops. There's no place where one of the magnetic field lines begins or ends. Which leads back to the idea that I can't get a pole by itself. A north or south pole can't exist. This is really different than when we had like charges and we were looking at the electric field, right? I could have a positive charge by itself, and those lines started at the positive charge. They had an origination point. For magnets, there is no start or end to the field lines. Instead, they just sort of loop around over and over and over again, okay? And the same thing is going to happen even if I try to split them in half. You're going to get the exact same looping sort of structure. Let me add a couple of points to this. It's just like what we had with electric fields. The density of lines indicates the strength of the magnetic field. As they're more dense, that's where the magnetic field is stronger. You will see that the lines here are the most dense inside the bar magnet itself, and they start to get a little less dense as you get farther and farther away from the magnet. Also, the direction of B is tangent to the B field lines at every point. Is tangent to the magnetic field lines at every point. And finally, we could say that the lines point in such a way that they exit the North Pole and enter the South Pole. And you can see that reflected in the diagram above. They're propagating outward from the North Pole, they loop around and come back in to the South Pole of the magnet. And if you want to see a more physical representation, I don't know, have y'all done magnetic field stuff in lab yet? I think you started last week, or was it this week? Last week? 2 weeks ago? No, it's different for different labs, right? So we're a little behind, but you've done some things. Have you done anything like this?
Yeah, no.
No? Yeah.
Something like
You did something like that with compasses.
Yeah.
Okay, that's good. So you've seen it. You now kind of understand a little bit more about what it means, perhaps. Another way of visualizing the magnetic field, and we have like more interesting tools for magnetic fields versus electric fields, I think. You can literally take little tiny light pieces of iron filing, shavings that are really light, And if you just throw them into the region where there's a magnetic field, they all feel that electric or the magnetic repulsion and attraction, and they sort of just like go and line up with the magnetic field lines, which means that we're literally seeing sort of these iron filings draw the magnetic field for us. It's like instead of this thing being invisible, you throw the iron filings in there and they all just sort of go and be like, here's the magnetic field, these are the directions it points, this is what it looks like. So with a horseshoe magnet like this, you can get some idea of what all of these field lines look like by comparison. If we were to take the iron filings and drop them on this, you would get these loop structures like so, all right? And I tell you what, you were good on that one slide, so I won't do the second slide I was gonna do. Congratulations. You survived 5 minutes. I didn't make you do 10. So like, go do some physics this weekend. Enjoy the 3 days, huh? Buy magnets, play with magnets, find the largest magnets you can buy online and just purchase it. Maybe a large superconducting magnet.
Put it right in my living room.
You'll have to feed it. That's the big problem. It doesn't stick around. It tends to go away.